Good afternoon. Today we will be beginning our fourth unit, which is recurrence relation. Now, before we move on to the concept of recurrence relation, we have to understand what does recurrence mean. So, earlier in the programming subjects that you have studied the term recursion. What does recursion mean? If we are calling the function again and again, then that is known as recursion. So, suppose to give you the most simplest example for recursion, which is the factorial, finding the factorial of a number. Suppose if you want to find 5 factorial and the formula for factorial is given as n factorial is equal to n into n minus 1 factorial. So 5 factorial can be written as 5 into 4 factorial. Then again for 4 factorial we call this function again. So 5 into 4 into 3 factorial. Then for 3 factorial, we call it again into 2 factorial, 5 into 4 into 3 into 2 into 1 factorial. And then finally, while we are writing our condition, we write it until 0 factorial is equal to 1. So in that case, we write 5 into 4 into 3 into 2 into 1 into 0 factorial. We know 0 factorial value is 1. Then we compute this. Okay. So this is the concept of recursion in the case of programming. Now, in the case of discrete mathematics, recurrence relation is basically you call the same equation or you call the same relation again and again until you reach some initial condition. So, we will study what is an initial condition and what is a recurrence relation. So, another example of recurrence relation is suppose the number of children in a playground. So, you have a playground or a park and the number of children in that park doubles every hour. That is, suppose if you have at 4 p.m. in the evening, if you have 5 children, at doubles every hour. Okay, so 5 p.m. you will have 10 children. At 6 p.m. you will have 20 children, and so on. So if a park begins with 5 children, how many will be present in n hours? So after n number of hours, how many children will be present? So to solve this problem, let an be the number of children at the end of n hours. An is number of children at the end of n hours. Okay. Because the number of children doubles every year, the relationship will be in this form. An is equal to 2an minus 1. And this is whenever n is some positive integer, given n belongs to positive integer. This relationship together with the initial condition that at 0th hour, that is if I am considering 4 p.m. to be my beginning, so then a0 is equal to 5. This determines uniquely an for all the positive integers. We can find a formula for an from this information. So usually whenever we have spoken about the different types of counting problems in unit 3, permutations and combinations, along with pigeonhole principle and principle of inclusion exclusion, all of those were concepts for solving your counting problems. So when we have some kind of counting problems which cannot be solved by using the techniques that we have discussed in unit 3. So instead of that, we can also use these concepts, which is recurrence relation. So recurrence relation is basically between the terms of sequence, as we have done using this example, the number of children problem. We will study a variety of problems, that is counting problems, which can be used using the recurrence relation, and we will develop certain methods to find our recurrence relations easily, and also formulas that will satisfy certain types of recurrence relation. Now, based on this, another thing to be remembered is what is the definition of recurrence relation. So, a recursive definition of a sequence specifies one or more initial terms and a rule for determining the next terms from those that are before them. That is, whenever we are speaking about recurrence relation, the simple definition can be stated as follows, that if you want to find the next term in the sequence, you will have to use the previous term. Okay, so if we want to define the recurrence relation, a recurrence relation for the sequence is denoted by an, is an equation that expresses an in terms of the previous terms. We express an in terms of previous terms, namely a0, a1 and so on up to an minus 1 for all integers n with n is greater than or equal to n0. A sequence is called a solution of the recurrence relation if its term satisfies the recurrence relation. Okay, so now to understand the topic, before we start the introduction for recurrence relation, what I will do is I will explain you the first topic, which is generating function of sequences. Now for generating function of sequences, suppose sequences of real numbers, as I have explained for recurrence relation, we have a0, a1, a2 and so on up to ar. That is a function whose domain is the set of non-negative integers and whose range is the set of real numbers. Expressions like ar is equal to ar from r is equal to set of ar, that is the set of real numbers from r is equal to 0 to infinity, denote such sequences. Now the example that I will teach is, suppose a is given as 2 power r is equal to 0 to infinity. So this sequence is basically the powers of 2 from 0 to infinity. What will be the sequence? The sequence for this will be, so sequence A will be simply 1, 2 power 0 is 1. Then 2 power 1 is 2, 2 square 4, 2 cube 8, 16 and so on up to some value r. Okay, and this is the sequence. Similarly, I can have another sequence B, which is denoted by br, r is equal to 0 to infinity. Now, where, what is the sequence br? It is denoted in this way. br is equal to 0 if r lies between 0 and 4, including 0 and 4. Okay. Next, 2 if r lies between 5 and 9, including 5 and 9. 3 if r is equal to 10. 4 if r is greater than 11. Okay. So now what will be this br sequence? It can be written as, let me write it over here, b0, b1 till b4 will all be equal to 0. So b0, b1, b2, b3, b4 is 0. After that, what about b5 to b9? They're all equal to 2. b5, b6, b7, b8, b9. They are all equal to 2. After that, we have b10. b10 is equal to 3. And after that, br for all r greater than 11. br is equal to 4 where r is greater than or equal to 11. Okay, so this is your sequence, or it can also be written in the following way. br can be written as 0, 0. How many zeros? 5 zeros. The first 5 terms are zeros. Then the next 5 terms are 2s. After that, we have a single 3 and then all 4s till infinity. So this is the sequence. Similarly, if we want to write another sequence, C is equal to CR, set of CR where R is from 0 to infinity, where what is the sequence? CR is equal to R plus 1. Okay. So R is equal to 0 plus 4. our first term will be 0 plus 1, second term C1 will be 1 plus 1 and so on. So this sequence is denoted as one, two, three, four, five. Basically, it is a set of all natural numbers. Similarly, I'll take another sequence D, which is equivalent to dr. Okay, I'll be using the capital letter for denoting the set of all numbers. That is how you represent it normally in sets, and also the small letter. So this is a small letter actually. The C is small c, dr, and dr denotes here set D. So dr is equal to, the set D is equal to dr set of numbers from 0 to infinity, where for each r, dr is itself equal to r square. That is the set of all squares. So in this case, what will be the sequence? The sequence in this case will be equivalent to 0, 0 square, okay. Then 1 square is 1, 2 square 4, 9, then 16 and so on. So this is the sequence of all squares. So the letter we use for the subscript, that is this r or this r, has no particular significance. That is, we can use either k, any other letter can be used. That is, there is no difference if we are denoting it with also di, where I is equal to 0 to infinity. You can use any letter. Normally, what we are interested is in the sequence where AR is the number of ways to select R objects in some procedure. Now, what does this statement mean? So, if we are talking about, suppose dr be the number of non-negative integral solutions to the equations. Okay, so if we have this equation x1 plus x2 plus and so on up to xn is equal to r, where n is a positive integer and each x is subject to some condition. So basically, whenever we are describing, if you remember in permutations and combinations, dr is the described as a number of ways of distributing r indistinguishable balls into n distinguishable. So basically, I'll just write this. dr is can be written as number of ways to describe number of ways to distribute are indistinguishable balls, that is similar balls, are indistinguishable balls into n distinguishable boxes. So there are R balls which are to be put into n different boxes, distinguishable boxes. So in that case, how do we write it? If R lies between 0 and n, it will be NCR. If R is greater than n plus 1, then it will be, we cannot put the object, so the answer is 0. So the polynomials involve different non-zero terms. We introduce the concept of generating functions, which is our topic that we are learning today. What do you mean by generating functions of sequences? So the use of generating functions is usually an abstract technique used to solve our combinatorial problems. Okay, so generating functions is basically an abstract technique. Now we will study what does a generating function mean. So generating function, suppose if we have our sequence a is equal to ar, r is equal to 0 to infinity. What do we do is we assign the symbol a of x, and what we will do is a naught. So r is equal to 0 means a naught. For a1, we will multiply it with the power of x power 1 again. So this subscript, we are using it as a power for x. Okay, a2 will have x square multiplied with x square, and so on. Similarly, an will be multiplied with x power n, and this goes on till infinity. So our sequence can be written in this form: r is equal to 0 to infinity ar into x power r. So basically what we are doing is, for our sequence we are multiplying each number with the subscript whichever it has. So if a naught, then x power 0. X power 0 is 1 anyway, so we are not writing it. So the this expression is basically known as the formal power series. This is known as the formal power series. Now, these are very important terms, as this cannot be explained in terms of definitions that can be written on slides. So, I am explaining it by giving this example. Very important terms. So, formal power series. The expression A of x is known as the formal power series. AI, that is A naught, A1, A2, and so on. It is the coefficient of x power I. Okay, this ai is the coefficient of x power I. Also, the term ai x power I is the term of degree I. It is the term of degree I. Okay, and the term a naught x power 0, which is simply a naught x power 0 is 1, is called the it is called the constant term. Okay, the first term is a constant number, it has no x attached to it. The coefficients are really of interest. Actually, we are interested in the coefficients, but it is usually easier to solve a problem when we express it in the terms of polynomials. So we are interested in the coefficients, and for this reason the formal power series is called an ordinary generating function for the sequence. So this a of x is also known as the generating function for the sequence a is equal to ar. Okay, this is ar written in this way: a is equal to ar and r is equal to 0 to infinity. Okay, so the why do we use the term generating function? What is the purpose of using this term? So the purpose of using this term is because in some sense a of x generates its coefficient. A of x is generating its coefficient, and it is also ordinary is also used because it is used to denote the fact that powers of x are used. Also, we use other kinds of generating function like sine generating function, etc. Now, so normally we don't use the word ordinary, we generally call it simply generating functions. And why are we using this formal? So we use the word formal power series to generalize it, to distinguish it. And the concept of power series is something that the students that you have already seen in calculus. So basically, if all of the coefficients are 0 from some point on a of x, it is just a polynomial. Now, based on this, we will see a few examples. Okay, so the generating functions examples. The generating function a of x is equal to r is equal to 0 to infinity. So we found in the earlier examples actually a of a is equal to 2 power r is equal to 0 to infinity, right? So for this, if we want to write the generating function, we can write it as 2 power r into, if we have 2 power 0, we will multiply it with x power 0. If we have 2 power 1, we will multiply it with x power 1. So simply we can write 2 power r into x power r. Or it can also be written as 2 power 0 plus 2 power 1 into x, 2 square x square 2 cube x cube and so on, or 1 plus 2 power 1 is 2, 2x plus 4x square plus 8x cube. So for a of x that we have already seen in the example over here, the generating function is this. Similarly, for b of x, we can find it out. B of x was, what is the series b of x? It was first 0, 0, 0, 0, and then 2, and so on. So till b4, if we multiply, I'll just write it so that you understand rather than explaining. So we have 5 zeros, 5 twos. Okay. So we will have 0 into x power 0 plus 0 into x power 1 till 5, if you remember. Till b4 we have all zeros. So we will multiply with 0 x square plus 0 into x cube plus 0 into x power 4. After that we have 1 into, not 1, in the question we have 2. So 2 into x power 5 plus 2 into x power 6 plus 2 into x power 7, 2 into x power 8 plus 2 into x power 9. Then we have 3 into x power 10, and then after that all 4. So plus 3 into x power 10 plus 4 into x power 11 plus 4 into, so from here we have all 4, so we can just write this. So basically b of x will be written as, all zeros will just not write it, so 2x power 5 plus 2x power 6 plus 2x power 7 plus 2x power 8 plus 2x power 9. So this is the generating function for here b of x. For c of x, you can just write it directly. R is equal to 0 to infinity. What was our CR, the sequence? The sequence was R plus 1. So R plus 1 into x power r, and b of x can be written as R is equal to 0 to infinity r square into x power r. So these are the generating coefficients or the generating sequences of your sequence A, B, C, D that we have studied. So if I want to define the generating sequence, I can define it in this way. Definition. Let a of x is equal to r is equal to 0 to infinity ar x power r, and b is equal, b of x is equal to r is equal to 0 to infinity, or we can write s is equal to differentiate ds x power s. So these are the two formal power series. Then we can define a of x is equal to b of x, first thing. If our term an is equal to bn for each n greater than or equal to 0. That is, our two series will be equal if each term is equal to the other term of the sequence. Also, we can perform multiplication by some constant c into a of x, that is, we are using some constant to multiply it. Then we will multiply each number in our sequence with car into x power r, multiplication by some number. Now, if we want to perform the addition of two sequences a of x plus b of x, can be done if we have n is equal to 0 to infinity an plus bn into x power n. These are very simple concepts, not something very complicated. And similarly, if we want to perform the product a of x into b of x, it will be equivalent to n is equal to 0 to infinity pn x power n, where Pn is equal to j plus k minus n aj into bk. That is, we multiply the coefficients in such a way that some of the our constants should be written in such a way that we are multiplying the subscripts. Now over here, for the last multiplication, I'll try to give an example. Suppose if we have a of x is given as a naught plus a cube x cube a3 x cube a4 x power 4 plus a8 x power 8. Similarly, we have b of x is equal to b naught plus b4 x power 4 b5 x power 5 plus b8 x power 8. Then we just mean that the coefficients are 0 for the missing power. So x squared, in the case of a of x squared is not there. Then x power 5, 6, 7 is not there. So that is basically the coefficients are 0. Now how should we multiply it? So what we do is we start multiplying it in such a way that a naught is multiplied with all the terms a naught, b naught, a naught, b4 x power 4. Similarly, the simple multiplication is done. There is nothing complicated in this. Now, based on this, we will see the generating function models. The topic name is generating functions models. That is finding the coefficient and also a few permutation combination problems, similar kind of problems to permutation and combination in the next lecture.